So I'm a faculty member at the Delft University of Technology and coordinating all the peer-to-peer research there. And so for the coming slot, I would like to explain the state of the art in peer-to-peer and also a bit what of the state of the art. But first, a word of thanks actually to the people that sponsor us, because the peer-to-peer group at Delft University is the largest around, and that's actually the only reason why we've been able to make things work, because these things cost a lot of resources. Getting search right, I'm standing here in the Google building, so I don't know, it's obvious of course, but getting these things right costs a lot of resources. And I'll be talking a bit about the context, the future of television in years to come, and what problems that creates actually for search, and the dealing with spam and the challenge of reputation, and a bit about the state of the art. So first, the context of this research. When we were going to a few years ahead, we're looking at a few million people who are watching TV on a small screen or a big screen, a 3D screen or something. A few hours of TV a day, a decent bit rate. And we're talking about a lot of data that's coming up. And these are realistic numbers. As people, we did some measurements, and we did a few million scrapes with our supercomputer of YouTube. We see these numbers coming up. So that actually means that searching this vast media cloud will actually be a challenge. And to put it a bit more dramatic, the importance of search and what you're exposed to is actually the media cloud is where society thinks. So it's not just about precision and recall and what comes up. It's actually, if you're exposed to the media and you're dealing with the media for a decade, this actually changes a bit what you're exposed to and what you're not exposed to. And the first search result actually has a long-term influence. It's where society thinks. So to illustrate that, I just have one slide on the dark side of this. This is a study on quality and reputation. As you have these user-generated content sites, which probably will be important for the future of TV and will only grow, that this sort of source and reputation and search quality is really interesting and really challenging and difficult, even if you're not in the peer-to-peer space. So you have central trusted servers to deal with. Then end of 2007 published studies. 153 videos investigated on YouTube on vaccination, immunization. There were a lot of them. The majority was positive. And yeah, come on, get that shot, get vaccinated. There were some negative ones, ambiguous. What's now the problem in this community? That the negative videos actually got more ratings for quality, and the quality ratings they actually got more stars on average, and they got a lot more views. So the negative things were more popular, even though they were a minority amount of videos. And these negative videos that had unsubstantiated claims that contradicted medical knowledge and sort of the professional consensus. So this is sort of, when we talk about search results and where society thinks, it's like people go to their doctor, they ask their family first, but then as some measure, they actually go to the internet. And what do they find there? And if they go to the peer-to-peer search, what will come up as the first video? That's sort of showing the dark side and the challenge that lies ahead to get this reputation. This is not new to YouTube, or just go to Wikipedia and ask for controversial topics, and you'll see that this is happening more. So in peer-to-peer, you have challenges are even more. No trusted central server or server cloud to ask things for. Peer-to-peer means it's a collaborative network, and you have small nodes and big nodes, big PCs and small PCs or things. So illustrated here with the elephants who have a lot of connections and the tiny mice peers. And this can be a network of millions. So I don't know how many people have experience with BitTorrent or EMEA or these sort of systems which are now emerging. And this will, as I was discussing on the future of TV slide, and this sort of technology is likely or is already included in televisions you can buy in China, and it will also go probably in the TV sets in the years ahead. So what you need to do is, like, if there's sudden flash crowd, it should not be that one peer-to-peer engine in one specific TV is suddenly overloaded, or one PC. So it should be load balancing the whole queries and things across all nodes. Another challenge is that you actually would like to exploit semantic clustering, keep this locality that some people are interested in certain content, and that you don't need to go to different continents to answer queries or to keep this overlay together. And that you actually rewire the network, that you do links. We had the cheese lovers overlay portion, and the people who have the sausage taste, sort of that they form a cluster together. But a problem with these things is the reliability. So you have node failure in peer-to-peer, and it's very slow. These machines which fail after a few minutes or a few hours. And what you have to do then is rewire the network to compensate for this. So in peer-to-peer, you have quite a challenge. So what we have is we want to have a trustworthy, reliable, fast mechanism for searching this media cloud, but all we have to work with is donated computer resources, which even can be fraudulent, spammers or people who misuse or just corrupt memory. And it fills in hours, so they're going offline and all these things. So they're really the opposite of a trustworthy server in a cloud. So quite some challenges. If you look at a bit more detail, the overall research question, what you want to solve, then integrity and trust, how to deal with spite and pollution. I'll be talking a bit more about italic things. Detect popularity in a fully decentralized way, also robust. I don't think this problem is never solved in a real system. How to do beyond mere file name. So what's now the state of the art in peer-to-peer search in real systems is just file name matching. Another big challenge is, how can we organize the overlay? I probably want to exploit locality, the semantic clustering, that things which are sort of together, that they're somehow expressed in the overlay. And network locality, that you have this low latency, that you don't need to go to the other continent for replying to searches. And also the social locality, as the web is going social, that probably if your friends are also in this peer-to-peer system, that they like this video or something, that you increase the relevance ranking or something, you promote that search result. One of the difficulties is for many years that if you turned off these peer-to-peer nodes or these applications, these clients, all state was lost. And when you come online again, you have to preserve everything, indexing and all these things. All the metadata was all lost most of the time. So persistent storage, but keeping it lightweight has been a challenge. So the project I'm coordinating is the first peer-to-peer client with a full lightweight SQL engine in it. Another challenge is how to exploit these terabyte hard disks. Also these routing tables, all these things, been proven very difficult to exploit that effectively. And one of the things with modern technology, like the swarming of BitTorrent, bigger swarms are better. But usually if you have a few, we've seen that you have 100 swarms of the same content, then you actually have fragmentation of swarms. Instead of a giant swarm with tens of thousands or 100,000 peers, then they're all fragmented into little swarms. That actually means performance loss. So this is also a problem which you should solve probably at the peer-to-peer search layer. Find not only the good content, but also the most healthy swarm. So how do people have done peer-to-peer search over the ages? In June 1999, there was the first real system built, the Napster, where, well, it was just central servers. There was nothing peer-to-peer about the search perspective. They had a bunch of servers, I believe, at the height. It was 50 servers. You just select one of the servers, and you do your keywords there, and you only get returned the peer who have a certain content. So very unsophisticated, very simple technology. A real system was launched in March 2000. It was more decentralized and not very sophisticated again, but it worked. You send your queries out to a bunch of people, they forward it again to another bunch of people, etc., etc. And actually, this system proved to be popular just for keyword matching. But this Nutella protocol, as it was called, actually literally flooded the internet backbone. There was more query traffic on the internet backbone than there was actual downloading with this protocol. That's how inefficient this system was, and also prone to a lot of spam. So there was not it didn't survive that long. Then we're going March 2001, where the Kazaa system was launched, where it was a bit smarter. Instead of these central servers or all this flooding and broadcast, you had actually more preserving of state and indexing. That from roughly 300 peers, this system automatically promoted a super peer, which is connectable and had a decent uptime. And then these queries, instead of being broadcasted to all of them, these 300 peers could be reached by this single super peer. It had an index of these file names. So you could just talk to one super peer, and then you also had a decent search results. But again, no solution of spam, because it had voting in it. You could rate it, but that was already very early in the Kazaa system. There was only one problem. You could just as easily inject fake content and spam as you could inject positive fake votes for this system. So it never worked in the real world. Then we're going a bit further in time, but in 2002 roughly, then because of previous failed attempts, no more peer-to-peer. We're going backwards in technology. Trusted web servers, so you just had when eDonkey links or BitTorrent links became popular, the web servers became the dominant form to access these things. So even though the downloading was exploiting the peer-to-peer paradigm, the search was still using, or was again using, central trusted web server with standard moderation feature and spam prevention. Then a bit forward in time, June 2007, another real working system. It's been talked about for a lot, and then there was an interesting study done on the DHT, where you use hashes. So instead of keywords or all these things, or indexing of file names, what you now do is you convert searches into hashes, and then you begin to search for those hashes. So it's a bit of a, you have a bit of indirection there, so it's difficult to do fuzzy matches or combining queries. But the problem was, again, nice idea, lots of papers published about it. But if you look at an evaluation of how this performed in the real world, yeah, first the scientist had to actually do some bug fixing because it was a bit too bad. And so a thing talked about for a long time, the DHT, the real deployed one. So you do a keyword search. This is not milliseconds, this is seconds. So 50 seconds of waiting time or 100 seconds of waiting time with a high probability. That's not what you want on the system. Imagine you have to search through videos in the pure peer-to-peer system that you would have to wait 50 or 100 seconds. So this is what the real world was like of peer-to-peer search according to this measurement. The months, or actually the years afterwards, they got it down to 2 or 3 seconds, which it is today. But still, you see that these things took quite a while to become mature. And something which are dozens of papers are published about that was not usable in the real world. It takes a lot of resources. So we'd like to talk now a bit about what we believe is the state of the art in peer-to-peer search. It's our own stuff. And one of the problems is that this takes a lot of resources to get right, and a lot of programming and bug fixing. So what you actually do at universities is we do bug fixing of prototypes and things that actually work and have thousands of users who actually try to break it every day. So that's not what a university is built up. And so it takes a big team. So we are bigger than we have more resources than most of the startups in peer-to-peer. So that's quite a problem. So that's probably the reason why not many people are working on peer-to-peer search. So we've been working on this for a while, and the algorithm is actually that you, instead of searching for boxes or for hashes or for things, it's actually what you do is you go towards the human side of things. It's been very challenging. We've been now working on it for 4 years and improving it. And so what you have is you take into account the taste of people, and what we have is an algorithm to determine the people who are on the network currently online who have the most similar taste to you in terms of previous download behavior. And then you have a bunch of random, very colorful people who are not like your very plain profile. And what you do is you send the query out. First you look at locally because everybody has a big index. But you send the query out to 10 people who look like you and to a bunch of people who will come up with colorful search results your taste neighborhood won't have. So you sort of have a lot to work with. One of the things we changed is that everybody has thousands of items already locally indexed. So this is exploiting the terabyte hard disk age, and this is made possible because a full SQL engine is bundled in our software. That's not very it's not very easy to do this sort of semantic clustering, finding peers which are similar to you. The basic idea is shown here in the slide that peer 1, 2, and 3 with the panda.mpeg and koala.mpeg, and that you see a bit of overlap between these sort of file names that these 3 peers like here. And then you put some fancy math to it, and then you can actually see in the user item matrix and all these things, you can calculate how similar somebody is to you when you meet them. And that's what we use. We cache the people around you who have the most similar taste. And we also take it to the next level. So instead of just keeping 1 or 2, like one connection open to a super peer, we keep thousands of people around us. We keep track of them just to improve these search results. So it's a very simple protocol underneath. You just this is the basic message content. You just tell which hashes you like, as indicated by a BitTorrent show one hash of a BitTorrent identifier, BitTorrent swarm identifier. Then you send around there's also public-private key pairs in there. We fully implemented elliptic curve cryptography. All this hardcore work that needs to be done. Then you give the public key and the current IP number of people who are currently online. And that was the person who was the most similar to you on the network. And then you give a bunch of random peers. So everybody's telling this to everybody. And what you can now do is crawl this network, and you give this message, and you get a message back, and then you go to the next one. So you can sort of crawl the network, and you get these thousands of sort of user item profile thingies. And then you have all these hashes, and then you also collect the .torrent information and all these details. But what you end up is that you contact a lot of people, and you can build a very interesting local database. So recently we've been able to add a click log functionality to that. So you even have the term in this. So this is beyond the sophistication of other peer-to-peer systems currently in deployment. And how this actually work for real searches. So you do a keyword search, and you asked a bunch of people around you, please answer this query. You already have a lot of metadata. You know who to ask. And this is now in seconds. So we have the median search response time is 325 milliseconds. So we had various versions. We've been at this for 4 years. So we had various versions of our software and improving it. And the latest push is now 325 milliseconds response time. And once you have these search results on your screen, then these are all just a bunch of BitTorrent swarms, and you want the best match to go first, and all this, the relevance ranking you can do. Then the user clicks on it. Then you actually want to see this video or start downloading this content. So you need to do another problem, and that's the how to find this swarm. So this is collaboration within the European Union funded project P2P Next. So in last December, there was a big open source code release, and there was a DHT implementation in there, which actually cut down the time in half. So if you look at just a bit of experiments, here you see the lookup time is now, let's say, 500 milliseconds or something. If you actually want to contact the swarm, it's now 500 milliseconds. So this is faster than the proprietary clients like MuTorrent do it. But just they're in the range of 2 or 3 seconds or 1 second roughly. So this is now acceptable for end user performance, and no longer the day of 2007 when it took 50 seconds or 100 seconds. So then you have this content, you can search it, keyword result, but then you have this problem of spam. Probably some sort of reputation system needs to be in place, or these things, because like I briefly said, the Kazaa system, you could just as easily inject spam, and you also just got lots of positive votes on it, so there was no sort of reputation system to keep it in check. If you can just as easily vote on content as you can inject a spam, then there's no effective mechanism in place yet. So this was 2001. So people have tried. One of the best examples is the really working system of Credence by Cornell. If you look at their webpage, they see that 920 young users have used it and actually started voting on the authenticity of peer-to-peer files on the Nutella protocol. So you can see that they never did an update or a new release, or this is a one-time project typical of academia. It takes too many resources usually to do a full-time update and work on this stuff for years, and it's difficult to get publications. So I don't have much publications. We have working system. So this is what you want in life as a faculty member. Working code, bug fixes, your papers. What this system did is you have to vote on the authenticity, and then you can discover other people who also voted on authenticity. And if you have some overlap that you also thought this was real stuff, then you collect these profiles and you begin to trust the people which you have overlap with. So you don't have these seal of authenticity directly, but through those overlapping peers, you begin to trust these things. So the challenge was that you have to bootstrap the system with real users, but also users have to bootstrap it themselves, that plus do a few votes, and then actually the spam engine begins to work. So that's that worked, but that's not what normal users want. They don't want to train the system for a few days. What we're launching today actually is some untested anti-spam technology, is where you can start a peer-to-peer channel. So in BitTorrent, fully decentralized, that you now have the concept of channels, sort of an RSS feed in peer-to-peer form, where everybody can sort of start a TV channel. So it doesn't cost anything. You don't need a satellite transponder. You don't need to buy some frequency on the cable spectrum, on the on the cable network. Everybody can start their internet channel, and you have these subscriptions. And if people subscribe to you, it's actually a vote, and these people who, if they're subscribed, they just, the default is that they broadcast their love for you on the peer-to-peer overlay. And actually all these people see that it's like, I'm hearing all people around me who vote this, and they all come from unique IP numbers and all these things. And then lots of subscriptions gives you a higher reputation of your channel. And then if you do content search and you have a file name match, and this is actually approved, and this is in a certain channel, then actually we increase the trust of this file, because essentially a peer-to-peer moderator, the channel owner, he actually approved it, and users approved it by implicitly subscribing to this channel. So this is all untested, but it's more sophisticated than what's out there. And then the challenge behind it, getting a step back. This is the general challenge of an internet reputation system, not only in peer-to-peer, but also look at eBay or all these things, that nobody has a really decentralized reputation system which can be reused for multiple applications. There's been, specifically for peer-to-peer, there's been no successful deployment and long-term use. A lot of ideas, nice in theory, but probably infeasible. It takes a lot of resources to get them where they are. And a lot of the proposals or the prototypes or actually deployed things, they sort of what I would call cheat using central components. Then this system is not self-organizing anymore. It doesn't have the property, if you do it right, of unbounded scalability, that all these 500 million TV sets in the world could potentially include this peer-to-peer engine and participate in the search. So this is a difficult problem that academia has not, or industry has not solved, I believe. So just 3 slides, and then I'm out of time. Good. Then talk a bit about the Bartikov, which is the decentralized, and which we've deployed and improved. So one of the basics is, like the previous one, that you're gossiping the protocol, your preferences around. What you here have, it's sort of a vision of a BitTorrent swarm or multiple swarm. It's just abstract. This is peers who actually have flow between them. So this is nodes in a peer-to-peer network. Could be BitTorrent, that's our case. Then you have, in a BitTorrent swarm, they have exchanged bytes. So they uploaded, node A uploaded to node 7, a big flow. If you look at node 5, then there's a few arrows here. And now the trick is that there's these flows, but everybody's gossiping. That's the small lines, the dotted line. So everybody's just talking. By default, you exchange also how many people gave you lots of megabytes and how many people downloaded from you. So very simple message. A node says 100 megabytes up, 80 megabytes down from peer 1. Peer 2, 600 down. Peer 6, 50 megabytes up. So what you have is everybody just sends around these messages periodically. You again collect thousands of them in your local database. You end up with a work graph. So how many bytes they actually uploaded and downloaded for you. And then you can use things like maxflow to limit flow. And what we use is this formula of the flow, subtracting up and down, to calculate from your perspective, if you have all these collected, these work graphs, these thousands of messages, that you can calculate the reputation of a peer. And then use that for content and other things. So how does this deal with flow? Well, so maxflow is a known algorithm that you actually need to have a direct, so even this dotted link, if there's they gossip around that 1,000 megabytes were exchanged, but that actually the real megabytes which exchanged, they limit this line. So you only begin to believe people you directly hear from. You believe them proportional to their megabytes exchanged with you personally. So this is not just theory, but this is improved and deployed since 2 years now. So a real work graph is shown here, where each node is a peer-to-peer client in our overlay on top of the BitTorrent network. So they are all fully connected in a full work graph where you can do nice mathematical properties on these things. And the beauty is that each line is a directed arc. See, these are two exchanges in a BitTorrent swarm, any BitTorrent swarm. So you abstract away, and now you have some nice things to calculate a reputation about. And you see also this isolated. This is the large cluster. Then you have these isolated nodes we're trying to deal, or the PhD team is dealing with these things.
So how big is the graph?
Well, after this new version launched, then we'll probably have another 10,000 downloads or something. So it's just the periodic of how popular, how much press attention we're getting. So,
so the basic principle of writing the standard is it based on actual traffic?
Yeah, that's the sad thing. So this stuff is difficult to get right. So I've talked a bit about relevance ranking, semantic clustering, that you have keyword search based on taste, and this voting, and that you have these channels in peer-to-peer. So this is the channels in peer-to-peer are now launched, and we have this search speed and this peer-to-peer RSS feed, sort of. So you can do voting on this, one per IP number. And the sad thing is that if you happen to have a few thousand or 500,000 IP numbers around, we haven't linked it. We're not able to link it yet with the actual work graph. This is still beyond our capability. So that's up for the next version in the years to come. So this is just to show you what's the state of the art and how much engineering is involved in these systems and how difficult this is for academia or other institutes to go beyond the state of the art here, as we're sort of building the future internet infrastructure for television. So I've talked a bit about the various search solutions which have been developed over the years, sort of with the central servers and the web servers, super peers. So there's a lot of ideas, but the resources are staggering. So we have more than 22 people in my team working on these things, both on the academic side and really bug fixing and tracing our Python code. So it's been 10 years of evolution of this field of peer-to-peer search. And the challenge is the complete decentralization. So we now have an open source system. So we hope that researchers will start to pick up on this, especially the problem of reputation and spam prevention. This is not many people work on real system, and we hope that our data set, especially this work graph, once it grows a bit and it's interesting, and it can people who work on the MATLAB side of things, that they will pick up on this and work together with us, that we get realistic algorithms we can deploy in the real world. So thank you for your attention. And I'm